vorweg, bevor wir starten. Wer von euch war denn letztes Jahr auf dem CCC-Camp und hatte einen von diesen coolen raketenförmigen Radio-Badges?
Es war nicht raketenförmig. Es war nicht raketenförmig.
War nicht raketenförmig?
Nein, das Radio-Badge war rechteckig.
Mist. Rechteckig. Okay. Schlecht recherchiert. Gut, sind doch ein paar mit dabei. Wir haben einen der Hauptverantwortlichen für diese Radio Badges heute hier und er hat sogar auch noch Unterstützung mitgebracht. Kleiner Applaus dafür.
Welcome to the translation for this upcoming talk about homemade high-security master keys by Michael Weiner and RF Guy. Your translators tonight are Flo, Hexor and Waffle, and we'd be very grateful for your feedback on Twitter using the hashtag C3T or tweeting it at C3Lingo. We also have an email address which is hello@c3lingo.org. And we'll be learning about how you can produce master keys for locks using mathematical processes and how we can use CNC systems to create these keys. Please give a warm welcome to RF Guy and Michael Weiner. Welcome from me. We're going to be talking about homemade high-security master keys. We're going to show you conventional locking systems, and many people have talked about those before, and we will show you two ways of building a master key system logically. Therefore, we're going to have the KESO system, which is a very common system. Ray has also talked about this before. We're going to have that for your comparison. And then there's the 3KS system, so 3-curve system, which is used in many buildings. It's actually quite a sensible system, and we're going to show you how you can analyze one of these systems and use mathematical and logical procedures to create the master keys for these systems. This is our agenda. We're going to give you a short introduction. Then we're going to show you the KESO 2000 system. There are several derivations of this, like Omega and many of these, but they all are based on the same principle. Then we're going to switch, and Michael is going to speak about the FR3KS, and we're going to show you our workflow, so how you can use a normal CNC, a very common device that you can buy for 1,500 euros, how you can use one of them to create a master key for that actually fits a given lock. There have been many things in the past. People started, I can use a tele lens to take a photo of a key. It's pretty straightforward. I mean, you have a key lying about. This is just a common key. And if I take a higher resolution photo of that, it's very simple. That can give me the locking code. The media talked quite a bit about the TSA keys, those that are used in suitcases. The first mention of them was in 2004 when Tobias wrote a short paper. I had them with me on the 28th Chaos Communication Congress and built master keys for some of those locks. And a TSA person had themselves photographed with a set of their master keys earlier this year. And there are also the American fireman keys, where the New York Times published an article about those keys alongside pictures of them, which was really nice because that allowed people to recreate them themselves. We're going to tell you how to. People have created drawers from photos and then 3D printed them. So you take a photo of the locking cylinder, so the part where you insert the key, and this allows you to build a 3D model, and then you can 3D print the matching key. That works pretty well. Another bit of research was the FRMCS, which has been analyzed by the Munich CCC a couple of years ago. And the advantage of a system, because it's magnetic, is that a photo doesn't allow you to derive the locking key. There are, of course, also some commercial variants, for instance, the easy entry profile device, where that actually have quite a few security features, because the services that get them need a locking, need a certain key for this, and it's not altogether cheap, but they can make a tidy profit on these, depending on the service that comes to open your door when you've locked yourself out. There's YouTube videos of how these things work. You use a certain blank for it, and then the blank is turned into a key based on the model. There are also milling machines for these. There's one made in China, and you simply enter the locking code, and then that's milled into a given blank. You can spend up to 20,000 euros for these. They're not altogether cheap, these devices. Another large database is Instacode, which is a software that you can rent from €7 per month. There's even an iPhone and Android app for it. And you simply enter the maker of the key, of the lock probably, and then it lists the profiles and lists all the commercially available blanks. There are several vendors who produce blanks independently of people who produce keys, and there's also a database of the keys, of the key codes. You might have noticed that many keys have a certain code on them, and you enter that number into the app, and then that gives you the key code for the key itself. So this is a nice database that you can rent pretty cheaply. You might even find the decentral security copy if you go looking for it. So this is a really powerful tool, and a commercial milling device can use this tool. So you just attach it via USB, you enter the code, and it gives you very detailed instructions. You insert the key into the machine, and then from that code, it mills the proper key. That's all available, but unfortunately it's pretty expensive. Many of you will have had this problem, that you didn't get as many keys from your landlord as you needed, and it's really annoying. You want more keys. So we wondered, what can we do to solve this problem? And today we're going to solve it with this 3KS. The first of these systems is the KISO 2000. There have been extensions to this, for instance this one, where there's a spring-loaded element in some keys. You can't see it in this picture, and it has to move. For instance, there's a little ball inserted into your key, and there's a magnet. That serves two purposes. The first of them is that it's easy to patent, so it's legal copy protection. So if I build something into my key that I have a patent on, nobody else is allowed to copy them. Some of these patents, sometimes patents expire, and then of course blanks can be produced. So what you do is you create a new system that has two spring-loaded elements, and you get a new patent, and that prolongs the copy protection by 20 years. Another thing you can do is that you integrate a trademark into your key. For instance, BKS or CES, which are the maker's names. You somehow integrate them into your key, and then you can build that into your key. You can copy protect that. Of course, it's silly. It just means that nobody's allowed to produce blanks. Nobody's allowed to produce blanks for these keys. And what we have with this system is it consists of a core, which you see at the top here. This is this little bar, and on top of that is a pin stack. This system comes from Switzerland, where these locks have a slightly larger diameter. In Germany, we have Euro profile cylinders, and they have this very characteristic shape. And this system has proliferated pretty widely, and therefore we don't have a lot of space. This bar here on top is where all the pins need to fit into. And you can see that there's a smaller, the size of the pins varies fairly widely. And the spring is on top of the pin, and it has to fit into that bar. There's a reason why you use these bars. This system has 2 rows of 5 pins. They're on the edge of the key. There are drill holes on the side on the side of the key as well. So as a permutation, I have 15 pins, which isn't that much for a locking system. Because if I have a locking system, I need to have several codes, because I'm going to have several keys, and several keys have to fit into the same lock. For instance, if you have an apartment building, you can have 15 keys that need to fit into the same lock, and I need to somehow build that into my lock. What you do with this system is, here you see the element on the side, and you see where the pins fit in. So a locking cylinder will check 5 of these dimple pins of these drilled recesses. And it's asymmetric. So there are several variations of this element. So I don't have 15 possible positions. I have 45 because I have 3 different key pin possibilities per pin. And I can't just use the positions for these. No, I have to use the positions for these, sorry. Another thing that they try to do is there are different kinds of drillings. Here we have a normal kind of pin, and it's because in KeySo the key is just simply rectangular, and I have a standard key with a standard dimple, and there's my layer of separation between the green and the blue part.
And at that point, we get back to the legal copy protection. We have different depths of drilling dimples we can put in there that we cannot create with a standard 45-degree angle. On one side, we have a pin that twitches, and that didn't work, but the manufacturers pretty soon just started building drills that work in different layers to make sure they could catch up. And the manufacturers of the keys again tried to evade that, and now it seems to be pretty much impossible to not drill that correctly with a drill. One other permutation they have introduced is having a straight pin that doesn't fall into the key, and depending on the depth of the drill hole in the key, I cannot turn the key anymore. Another case is we have, again, that stacked, that layered drill holes, where the pin again falls too deep. Here is another case of a layered drilling, and the pin, in this case, doesn't fall deeply enough in the pin. And for this special shape of the pin, I need a matching shape of the drill hole in the key, so the pin correctly fits within the key. In many cases, we also, for houses where different keys have to fit the house door, for example, not all of the drill holes are actually used. There may be a blind pin, and independent of which key is inserted into the lock, that pin doesn't affect the lock operation, in order to have the same core of the lock and have different keys able to access it. So at this point, we usually have a locking system in an apartment building, but in big buildings, we might have one general locking key with a master locking key which can open everything. For example, there could be different groups. For example, in a school, teachers might have one set of keys, and there could be other rooms where only the pupils are allowed, and other rooms where facility managers could get in, but teachers could not. So we have the difficulty of finding out how can we get to that general master key pattern or code. And to do that, we have to develop a method of determining how to find the locking code, how many possibilities we can take into account to get there. In principle, we have two information bits. We have the keys. Let's assume we have different keys. I have one key for my office that only fits that door, and because I would like to run some espionage or annoy a colleague, we're just talking about possibilities here. And how could we then continue? Now, the first problem is we need to take into account the method how the locking system is built. Because I cannot build different permutations into the locking mechanism, in that system, I only ever have the information of one key within the lock. Now, the superior key, the one that gets closer to the master key, has more drill holes. That is one remark is with the Kessel cylinder system, there's only ever one valid position for the pins in the cylinder. Between the pin of the case and the pin of the lock, there's only one layer of separation. As an example, here we have one key, and the information I can gather from this one key is exactly this one key and nothing more. Now, I take a picture of the key of my colleague. In this case, I see different drill holes. And I have now already moved that information to the key on the right. Now I get more information from the key of my colleague, and this key will at least open and close two doors. Mechanically speaking, my key space is limited, so I have to check which of the dimples I can add and might not add all of them. Adding a third key, I can add again the different holes in the key, and that is by far, those three keys are by far not all of the key space. Now, but still, I am now at I have achieved my target because I have a key that is superior to all of the keys I had before. And what I don't know is how much more there could be. What I see on the key on the right, at this point, there is no drill hole. So there could be something there, and there is a pin there that would like to have one given position. On the edge, again, we also have drill holes, but because the edge is so thin, there can only be drill holes at different positions, not different depths or different kinds of drill holes. Now, to Michi, who will tell you a bit about 3KS, about the 3-curve system. And as you can see on the picture of the key, you see 3 curves, one double curve of the upper and the lower curve, and one final curve, a third one that is a bit lower. On the right, we have a closing cylinder that is consists of a couple of movable pins and the sidebars. And there are 3 coding elements, holes in lengthwise grooves in the edge, as well as the curves in the lock. The key is quite rectangular, and I don't have that many variations in the profile. And on the side, by adding different grooves, I can change the profile, but that is purely passive. So if we just remove the edge to some point, it just fits anywhere. And then the side profile, this sidebar on the right side, when I turn if I insert the key into the lock, it just tries to be pushed down to the right position, and only if the grooves are in the right position, that is done correctly. But that works completely passively, so if I removed the whole edge, it would work perfectly. But the interesting bit are the curves. They move those sliders on the right side, these 6 sliders, to left and right, and only if these sliders have the correct position, then the sideband can be depressed. On the lower part, you see the key. In this example, it only has 1 curve, and that curve moves the slider. If I insert the key into the lock, the force is applied onto the sidebar that is pressed inside, and only if there is space in the slider for the sidebar, then I can turn the key and open the door. You see a small cavity on the right. It's a fake cavity. So if someone tries to pick the lock, if they turn it a little bit, the sidebar would get jammed in there and the lockpicker could not pick the lock. Now, if we look closer at the curves, because we want to drill these curves, there's 6 sensing positions, spaced 3.5 millimeters, with a distance of 0.5 millimeters. From one to the next valid position is half a millimeter, and the width is 1.2 millimeters of the curve. Now, each side contains 6 positions per curve. Within the lock, only every second position is being sensed. It is single, double curve, and on the other side, it's exactly the opposite. So we could construct a key, and we have done so, that works on 2 different locks. Now let's look at that double curve. There's 7 valid positions. The curve is half a millimeter deep, and this is the global configuration. This only changes if you have really big locking systems on higher hierarchies. For example, if you have a company that has an R&D and a sales department and these two departments, they could have different double curves. For example, 3KS key service will receive for their area an exclusive own profile, and they receive key blanks and have the exclusive license for that area. That used to be their profile for that key service, and they get a passive matching sidebar, so that way they can only determine the single curve. So yeah, key services usually, locksmiths usually receive the fixed double curve and only have to change the single curve. We have tried to propose a notation there. We call that curve D, and then have positions 1 to 7. 1 is to the very left, and right is to the very 7 is to the very right. 3KS Plus has two successors now. 3KS Plus, that's about 10 years old, and 4KS that was just published on security conferences now, and there's only a marginal difference. And the reason for that, for the successors, is that the old patent for 3KS has expired, and 3KS Plus is valid for another 10 years. And that way they try to keep up those legal copy protection, but to us, the difference in creating keys ourselves is marginal. On 3KS Plus, the position 6 is a bit wider, so a standard 3KS key would not fit in there. Similarly, a 3KS Plus key would not fit into a 3KS lock because there's a ½ millimeter difference. In 4KS, the double curve does not continue to the last position, to the top, and starts only at the other.
The single curve, there's only 9 possible positions, and this is the local configuration. It's 1 millimeter deep. The notation that we suggest here is S for single and then numbers 1 to 9. And 4KS differs in that it does not, that a double curve is not thicker, but the curve at position 6. So the slider is simply thicker at this position. The pin is thicker, and if I want to insert an old key, I can't because the groove on the side is too narrow, so you can't insert the key all the way into the lock. It only goes in up to position 5. That's all there is. And here we've taken apart some sliders and scanned them. And because of the scan, they're mirrored, but it's also easier to read them that way. This is a slider that only fits in position 1. Here's a slider that fits in 3 positions, so 1, 2, and 3. 1 would be here, 2 would be in the middle, and 3 on the right. This is one that would fit into 2 positions, 2 and 6. And if you don't want to open an area, but just 2 positions that two separate positions, they have to be spaced apart because otherwise it wouldn't work. And this is a larger case that would fit into 2, 6, 7, and 8. And with the double curves, we have we struggle to find sliders that fit into more than 1 position, but we found one that fits into 4, 5, and 6 at the bottom. This is because our space is limited. We only have 7 positions instead of 9 that's in the single curve. And you can see the difference between 3KS and 3KS Plus, where these grooves are slightly different. That affords you a patent. Hooray! Yeah, this part here is supposed to be the same width, but it's shifted slightly to the right or to the left, and that grants you a patent. And the question is, if we have several keys in several cylinders. How can you decode this system? So how can we take several locks and several keys and derive one key from this that fits into all the locks that we can already access, and possibly even more? If the key is your source of information, then you can take two keys, put them next to each other, compare them, and you see the two keys at the tops, the two positions at the top, and they differ in the middle positions. What do we get from this? If they match, then we know that they're at least in the same layer, but because there can be several valid positions in the same lock, we can't say if there might not be another valid position. That's where it differs from the previous system where it could only have one valid position, and I varied the position on the key, but in this system I have 9 different positions, and there are sliders where all 9 positions fit. And it's even worse when the positions differ, because we can't learn anything from that. It doesn't limit our search space, so all positions could still be valid. We simply don't learn anything. Either way, we don't learn a lot from it. We don't gain a lot of information. So let's have a look at the cylinder. Each cylinder delivers all valid locking codes. That can be quite a few, sometimes more than 70, but if you take several cylinders apart and you take the intersection of the valid codes, then that gives you the master code, a master key. Here's an example. We bought a system from eBay and decoded it. We took out one cylinder, and here we try to decode it. This is D for double curve, which is sensed alternately, 3-2, 7-7-3-2. The double curve is already fully determined. The single curve gives us the possibilities 1, 2, 3, 2, 6, 7, 8, 3, 4, 5, 4, 8, 5. This is obvious, and 7, which is also determined. This gives us 72 remaining combinations. If we do the same for the next cylinder, we already know it's a double. We already know the double curve, but the single curve gives us different possible combinations, and that excludes quite a lot of combinations. We only have 6 possible combinations left. And we do the same thing again with a third cylinder, and we're in luck because the intersection of 3 cylinders is already enough to derive the master key. The last remaining combinations, the last remaining uncertainties have already been excluded. So we're done. We have the master locking code that you can see on this slide. I'm not going to tell you that this key protects my apartment. No, of course it doesn't. But if you were to rebuild this, you could open certain locking systems. And so we scanned the master key as well and decoded it. And of course, the single code is 365457, which is exactly the same code we just derived. So we've decoded a 3KS system. How do we get keys? In our club, we have a CNC, an engraving machine. It's pretty cheap. It's bought from China. It costs us about 1,500 euros. It's 50 micrometers reliabilities, which isn't quite, and the area isn't quite enough for milling a key, but it's more than enough for milling a key, but it's all we had. So how do we go about this? What software do we use? How do we position the keys? These were new questions for me as well. And what we did is we used OpenSCAD and Inkscape. OpenSCAD is something that allows you to build text-based 3D models, and there are quite a few export formats, but we used STL or DXF. Inkscape is a 2D vector graphics program, and it's very versatile. And we used it to scan the keys and redraw the curves and measure the curves and check the distances. Scanning is a very good approach for characterizing keys because it gives you size information. And this was a funny event because the instant code is, you can only look at 3KS if you have an authorization from the vendor because it's secret. So we just went about and measured it, which isn't too hard, really. The CAD software describes the model of an object, and now we have to convert it into milling data. That's what CAM software is for. And I eventually settled on CAMBAM, which is commercial, but they have free licenses for hackerspaces, and it's pretty good for what it costs us and what it can do. You load the data from Inkscape, and it exports to G-code. And as a second step, we automated the most difficult step. This is CAMBAM. This is the entire key, the chaos knot. We drew all of that in Inkscape and then imported it into CAMBAM. And initially, we also drew the curves in Inkscape and then imported them. So you'd use a grid to align your template curves. We already have the right distances for the double curve here. You import that into CAMBAM, and then you can mill your key. But this takes a lot of time. So if you do it manually, it takes you 10 minutes per keys, or 5 to 10 minutes per key, just to have the milling data. And the most time-consuming thing was the export of the new geometrical curve and the import into CAMBAM, and then setting all the data, the diameter, the depths, and all of this. So we thought, could we maybe automate that? Our initial approach was using scripts to automate Inkscape and CAMBAM, but we didn't get very far with that. And then the idea was, let's just write our own G-code generator, and I'm going to give you a short demo. What you see here is the template that contains the data except for the curves. We always have this groove in the middle, which makes sure that the key stays in the lock when the key is being turned, and there's the sidebar that is being inserted from the type. And if the key is correct, it has two grooves that block the key, which prevents you from pulling the key at the wrong position. And we have these longitudinal grooves that are passive. You can just mill them, mill the same ones on each side, and then it'll fit any lock. So the sides are passive as well, so if you don't want to bother decoding them, you can just mill a groove at each position and it will fit. But the most important thing, and it's still missing, is the curve. So we bought a demo system that's also used for locksmiths. We decoded it, and this is what we got, the single and double curves. We wrote a simple G-code generator in Python. It wasn't that difficult. It was just refreshing some geometry, but not too difficult. We just copy the data, we paste the data into that. We export it, and it generates the G-code. And we have the new file. Where is it? There it is. I also created a backup in case it didn't work, but I can now import it. And there's my curve.
And that saves me the trouble of having to export and import that through every program in the toolchain. Now moving on, if I were to type in another code, that would work just as well. So if you need a key, now, having the software, there were some open questions left, and we moved on to the hardware. The question was, how can we position the key more precisely enough, and how can we mill on both sides? The precision is enough, but because the key is being sensed from both sides, we need to position it exactly the same, milling the other side. That question was solved pretty quickly. We just used brass for the keys. That the mill is strong enough for that. In the first couple of attempts, the sensing was a bit difficult. We killed some drill bits for that, but now we've arrived at a point where we can pay about 10 euros for a blank and have a working key. We usually use brass or steel for locking systems. Usually manufacturers might use a new silver. That is a bit harder. We could do that as well, but that would take us about twice the milling time. But our keys are a bit softer. They still are work in practice. So we thought, well, positioning blanks, the simplest process would have been to just create a jig. No, we build a jig, and with a goal of having the key positioned correctly with regards to the y-axis. In order to sense the position of the drill bit, we need an electrical contact between the drill and the blank. And in order not to have that, the material for the jig should not be electrically conductive. And we wanted to have the jig, we'd be able to fix the jig in the mill, regardless of whether there's a blank in it or not. I'm going to now show you the 3D model of that jig. What you see here at the bottom is a nose that fits exactly into the recess on the mill, and the holes on top are there so we can fix the mill to it, and we will place bits in it to fix the blank to the bit. And here you can see that jig in detail. What you can see is a blank on top of the jig, and there we have a triangle. The key needs to be fixed well.
Und da wird der Fräser abbrechen, das wird sich verschieben. Deshalb haben wir vorne noch dieses Loch vor diesem Dreieck dran. Und man sieht, wenn ich es jetzt umdrehe, sieht man hier hinten diese zwei sechskantigen Löcher. Das sind einfach diese Gewindehülsen, die sind von hinten reingesteckt. Und durch das Holz ist es einfach isoliert. Wir wollten erst ein POM-Material nehmen, aber das hier ist ausreichend stabil und funktioniert problemlos.
Ja, von dem Kunststoff hatten wir einfach nicht so viel da und dachten wir, machen wir erstmal ein Modell aus Holz, und es hat eigentlich ausgereicht.
Ganz normales Multiplex-Material, nichts Spezielles.
We use that.
Okay, gut. Wie sieht der Workflow dann zusammensetzend aus?
Finally, how does the hardware workflow look like? First, we need the blanks. We can either mill these or print them. Laser cut them, or we can buy commercial blanks. Another possibility is, and we'll come to that in the end, we had someone laser them, and if we were to produce keys in a larger number, we could have them punched. The original keys are 2.1 millimeters thick. We used material with a thickness of 2 millimeters, and that works as well. As a second step, we mill the key, the curves, and the edge grooves, and finally the mechanical fine precision work, removing the leftover bits. And we have a little demo prepared here. Of course, you can see the model here. That is an entirely normal lock from the locking system we bought. And I will show that to you in a second on the scanner. Those are two different systems. Here I have the key that I got with the lock, as well as a key from the demo, and because the single and double curves alternate, I can create a key that has two different sides, and if I turn it one way, it doesn't work in the lock, and if I turn it the other way, 180 degrees, it works. So we can really have two completely different locking systems with a completely different profile. This key has grooves on both sides. That one on the side, I have a pick here. Here on that side, and here on the other side, it's drilled in as well. That is the Passepartout that works with any 3KS lock for any system. Now, I hope you can see this. The lock now closes, and in here you can see the U from the sidebar where that needs to move. And if you look exactly, you see that they are exactly aligned. Now, if I turn the key, you cannot see that perfectly, but you should. There is a spot where both of the holes are misaligned. Because I did that in an asymmetrical fashion, I have different locking codes. It works that way and doesn't work the other. Back to the talk. One point where we saved us some work, the side grooves on the edge are only checked in one position, and if we had wanted to do this correctly, we would have had one of the edges with a code from one of the systems and the other edge with the other, but because that is the system is passive, we just took the union of the grooves and milled both of them. As you can see here on the profile cylinder, the key only ever sits on the lower side, and I can use the control groove to see which side of the key I should be using. So if you know a facility manager who has to manage two buildings, you can now build a key for him. And if you can sense that using the groove, if someone asks you, do you have a key for that building? You can just check the groove and insert the key in the correct fashion for it not to work in the building and say, well, no, it doesn't work. I don't have a key. Now, handing back to Jan.
We're going to carry on with this. We're not nearly done with this. We still need the perfect name for it. Maybe all keys are beautiful. We'll think about it. We're going to carry on anyhow. The first step is going to be the milling device. I think we're going to publish some code on GitHub, and we're going to publish the link so you can find it. We can optimize the whole thing. We can build a tool that automatically turns around the key. We've also improved the system to automatically calibrate itself. And of course, we could mill other systems as well. I just need to change it into my G-code generator. I just need to add a setting. And of course, a conventional serrated key, you can insert it horizontally into the mill, and then you can just mill the code into the side of it. And all this too could be automated. 3KS is not an insecure system. It's still very good. It can be manipulated. I'd say that this building contains at most 10 people who could do that, though. And there's a very simple way, there's a very simple method. If I have a mechanical key like this, it's my password. This is my password. And if I show it to you, I give you my secret. There's a very simple method of protecting my secret. I have one of these key pockets, and wherever I go, I keep my keys in this pocket. The system is not bad, but it can be manipulated with a simple method. You can just use liquid metal to cast a new key. And of course, the locking code is on the key itself. You need to protect that. I can buy one of these pockets for €5 anywhere. I put my keys in that, and I take it out only when I open my door. And that maintains my security. One aside, we have the milling device with us and would like to show it to people who are interested. We found an empty space next to the knock help desk. We'll be there in 10 minutes' time, and we're going to have the milling device there. We'll show you all the parts that we have. You can look at them. We can also mill some keys to show you how it works, and we're here to answer your questions, so ask them and we'll be happy to answer them.
Vielen Dank, ihr beiden. Wir haben jetzt noch ein paar Minuten Zeit für Fragen und Antworten. Wenn ihr Fragen habt, bitte geht zu einem der 4 Mikrofone, die hier in den beiden Gängen stehen, und sprecht bitte laut und deutlich rein. Wir fangen mal an mit einer Frage von den Online-Zuschauern.
Okay. The question is? Nein, das war nicht okay. So, jemand im Internet sagt, er war mal einem Schlüsselhersteller vermutlich in der Schweiz bei einem Vorstellungsgespräch, hat dann eine berechtigt kritische Frage gestellt und saß dann wohl ratzfatz wieder vor der Tür. Und jetzt ist die Frage, ob es Fälle gibt, wo zum Beispiel eine Bohrloch-Datenbank mal abhanden gekommen ist.
Also es ist so, zum Beispiel in Instacode, viele Hersteller geben diese Daten freiwillig heraus.
Many vendors actually give you that data voluntarily. For instance, Masterlock has serial numbers on the back of the device, and if you enter it into their tool, it gives you the opening code. Some are found out by reverse engineering. Some have very simple mathematical methods of where you can, you just where it's derived from the serial number. I haven't heard of leaks of these databases, of leaks of data of locking systems. Many vendors simply have a random number, and then they attach that to a system number, and it's system number 17 or something. Of course, if there were a mathematical system behind it, that would be troublesome.
Ja, kein Problem, da kommt ja keiner dran, wenn ich das sicher verwalte. Aber jetzt
databases are actually secure if they're kept safely. I haven't heard of any mechanical systems where that would have happened.
Okay, danke. Einmal hinten links.
Thank you. I wanted to ask if you tried to mill the first variant of the key.
The first 3KS variant?
No, the one with the single markings.
No, I just did it on my drilling device. You can buy them on eBay. It's usually used by locksmiths. I inserted a single key. The one with a different drill holes on the other side, and I just made it mechanically. It just costs you 300 euros or so to buy one of these machines from China.
Thanks. How realistic is it to build a skimming cylinder? For example, for the trash building.
It would be simpler to install a camera next to where the key is inserted. I have all the information on the same side, so if I had a very high resolution camera and I could recognize when the victim inserts the key into the lock, because I usually don't hide the key, I take it in my hand and insert it like this. That works. Mechanically sensing the key, that won't work. There's not enough space in one of the cylinders, but with a camera it would be very simple. The resolution is enough.
Next question. I have two questions. First, how many attempts did you have to do to get a first working prototype key? And the second question is, in the current stage, how long do you need to mill one key?
I think it took us 3 or 4 attempts until the first key fit. We had some trouble with thickness. We tried with a 3mm blank, but that didn't work. The calibration was a bit difficult. The problem is that I never really learned metal processing, so I learned it by doing. Generating the curve itself was no trouble at all. I think one side takes us about 5 minutes, something like that. Yeah, we've perfected it. Up until the Congress, we filed these sidebar codes by hand, but now we can just insert it into the jig. It takes 5 minutes to mill, we turn it over, we calibrate it automatically. It's still a bit tricky to do it without calibration, and it mills the sidebar code. I need to cut off the tip. It takes 2 more minutes to perfect it by hand, so it takes less than 15 minutes.
Thanks. Another question from the live stream. The stream would like to know if and where one can get the t-shirts that you guys are wearing.
That was a spontaneous action last Wednesday at the lockpicking event in Hamburg. The team made them for us, the team that makes all the signs as well. So just ask me, the design is freely available. We ordered them by express on Thursday and they arrived in time, so no problem at all, just send an email and we'll help you. Mine was just coincidence. I found it at a tourist shop in Barcelona and never afterwards, but I don't know where it is. So if you're interested, I can tell you where to buy one of them in Barcelona.
Thanks for the shopping tips. Speaking of the queso system, if I have a lock where the pin always matches, regardless how deep the hole is, if I drill a hole and have different keys, knowing I don't know how deep the hole in each key needs to be, and I cannot tell how deep it must be. How? Do you have any tricks?
These blinds that we have in there, the blind pins. The one at the bottom. I use these if I don't use the drill hole. Of course, I have no way to know. The key can still have a drill hole because it needs to open a different lock. If I just use it for one lock, I have no way to interpret anything. It's simply an unused drill hole because I always need to have 15 drill holes. But if I don't use it, this blind has to be in there. I can derive no information on whether the key has any hidden information in there. Some keys have fake information that still have a blind pin, but at some point in the locking system there is a pin that has a different height at that position. If this could cause trouble otherwise.
Is that being done?
Yes, absolutely. This is being used as a trap as well in larger systems.
A couple last questions. One. The curve system. Did you take into account that in the cases where you didn't know if there's a 5, 6, or 7, did you take into account that some possibilities could be excluded because the state transition would not be possible?
That's a question. Of course, the vendor can insert a slider that allows for anything. Those exist. Oh, you mean the diagonal milling of the key? It's always possible because we only check every other slider. This is the first double slider, but the next one is only checked here.
So it's always possible to move from 1 to 7?
Yeah, always can, because there's the other side as well. I also received the feedback that the maximum angle should be below 45 degrees, because otherwise it's no longer works nicely. The systems that we tried, we were just in luck, and they obeyed this rule, but otherwise just try. I don't know if it's specified by the vendor. I think it would just be a bit trickier, but still work.
Okay, go ahead. I would like to know how illegal it is to mill a key myself, or if it's only illegal to use it.
It's very straightforward. If I am the rightful owner of the key, which could be because I was handed it, or because it's the key to my apartment, that's fine. A locksmith gets in trouble if the key is patented, but as long as I destroy the key at the end and or hand it back, there's no problem. The European Court of Justice had a ruling on this as well. The key is simply regarded as a replacement part. As long as I don't violate any patents, I can have a key. Of course, if I make a key that allows me to access rooms that I am not allowed to access, then of course that's a different question, and I can get into a lot of trouble there. It's criminal, and I would think very carefully if I would want to create a master key for my company and just, walk through their rooms.
That would have been a question. If I create a master key of several keys that I own, would it be illegal to create that key, or would it be only illegal if I use the key?
If I use it as a proof of concept and I put it into my, if I just keep it well locked away, but if I give it to other people or give the locking code to other people, then I open a security gap for the person who has the master key. You can use it as a proof of concept. We just used a used locking system from eBay, and also the keyser system we used is something that was gifted to us. That's fine, but you should think carefully about it. We just wanted to show you what's possible. Protect your keys. I can take apart some of these locks without the key. These are always simplifications. The best system is that I have a separate key for each door, which is of course uncomfortable, but it's still the most secure method.
Thank you. The last question comes from the live stream. Someone is asking, if I have n keys, can I create an individual key? And that person has an old locking system with a couple of keys and a couple of locks.
Prinzipiell ist alles möglich. Wenn ich zum Beispiel eine gebrauchte Schließanlage kaufe, habe ich auch mal gemacht auf dem Flohmarkt.
If I buy used locking system, and I did this before, I didn't have the master key, and I took it apart, and what you often do in conventional systems is that the keys that need to fit into many locks are quite slim and narrow. The thing I see at the front is, well, there are keys that fit into any hole, and some keys don't fit into that hole. But I already see where I need to take away some material to make it fit. So in most cases, it's possible to create the master keys for given systems as soon as I have enough information to do it. If I have locks that are from all kinds of groups, it's going to be difficult, but it's possible in principle.
Thank you very much. A big round of applause. And this concludes our